Okay, today we're going to be starting to learn about the photoelectric effect and wave-particle duality. So, what is the photoelectric effect? Now, if you have this simple setup, here is a closed container, and we have here a zinc plate, so this is a zinc plate, and down here we have a gold leaf. Now, if we take a plastic rod and we rub it, so this is going to become negatively charged, and we bring it to our zinc plate. So what then happens is we will have electrons here, and they will travel down, and they will the negative electrons will travel down this metal rod here, they will travel to our gold plate, and because the negative electrons will repel each other, you'll have negative electrons here and you'll have negative electrons here. And you'll see the gold plate, the gold foil lift up. Now let's say you shine a torch on this, just white light. Nothing happens. But what happens if we shine UV light? Our foil will drop. So if we shine UV light, our foil drops because the UV light gives the electrons enough energy to be repelled, repelled off the zinc plate. We basically discharge this setup, and this is able to drop. So the UV light gives enough energy to the electrons to discharge the foil. Now this is very strange. What you're seeing here is light being able to cause an effect to electrons. Now, to understand this, we need to go back to what was happening in the physics world in the late Victorian time and the early 1900s. We had Max Planck, who was a young German physicist, and when he first graduated from university, the two fields the main fields of study in physics were both thermodynamics, which is the study of heat, and electromagnetism. As in electricity, and Planck wanted to work in both fields. He wanted to see if there was a connection between these two main fields of working, and in doing so, he stumbled into this whole idea of energy and how heat works and what is heat. And he proposed that he proposed that, well, radiant energy is emitted or absorbed in discrete amounts. or packets. At that point, people were looking at how a body, something that was hot, how it emits energy, and they were perplexed by the amounts of energy different bodies would emit, and it didn't really fit in with the theories that they had. So Planck's way of getting around this problem was to say, well, if energy can only be emitted or absorbed from something in discrete packets, and that the energy is in direct proportion to their frequency, and this idea worked. And if you divide the energy by the frequency, we come up with the constant of proportionality, which became known as Planck's constant. Going to be a K, not an H. Which is, if I can just find the actual value for it, I have it written down. I don't have it written down. It's tiny. Oh, here it is. So Planck's constant is 6.6 times 10 to the minus 34 joules per second. Joules second. And this is this proportion of this constant proportionality. It tells us that the relationship between the energy of a packet of radiant energy is equal to Planck's constant times the frequency in Hertz. Now, if we take this back to this demonstration, when we've got white light is got a smaller frequency, than UV light. So the white light gives a smaller amount of energy to this zinc plate, whereas UV light has got more energy because it is higher frequency, and therefore the energy that it is given can cause the electrons to be emitted. Now, Planck didn't explain exactly what was happening in the photoelectric effect. Before this was all explained, just get a new page up, another physicist, Heinrich Hertz, was studying electricity. And he also observed the effect that light can cause electrical current to be produced in a wire. Now, his assistant, what was his name? Philippe Leonard. This was his research assistant. He took the study much further, and he built this following apparatus. So if we have a kind of arc here, we've got a variable power supply. And we've got a very sensitive ammeter, it's microamps. Oops. This is a terrible circuit diagram. And then here we have a here we have, again, it's very similar to what we had just now. So this is a photocell, which incidentally is the same principle as what we have in solar panels today. So here we have, coming in here, you'd have a light source. And it reflects off here, of this plate. So this is our incident light. And this is a variable power supply. And this is causing this surface here. So we've got electrons, and they'll be here. This causes this plate here to act like a cathode. And what Leonard did in his experiments, he would use different intensities of light, different wavelengths of light, and he studied how this affected the current that was in this circuit. So he illuminated this metal cathode here, which is negatively charged, and this then causes, when the same idea with our previous experiment, if the wavelength of light is correct, the electrons are emitted and they will come up onto this circular arc plate here, these photoelectrons. And then you get your current flowing, and you can read your current, and you can read your voltage. He was able to measure a range of currents because he chose such a negative setup. Now, Hertz, and as he began to first study these, he had some assumptions of what he expected Firstly, they expected to see an increasing the intensity of incident light should cause an increase in kinetic energy of the electrons, and so emit with greater average velocity. Secondly, increasing the frequency of the incident light should increase the average velocity of emitted electrons. And for very low levels of incident light, it should take some time for an electron to gain sufficient energy to be emitted. Now, Hertz was basing his assumptions on a classical model of physics. he was looking at this from a thermodynamical standpoint. So in thermodynamics, say you had some cup of water, and you give those the particles in that water more energy, their kinetic energy will increase, and they'll move more vigorously within that cup of water. And within that cup of water, those particles will have a range of energies. Some will be very energetic, some will be less energetic, and as they collide and bounce into each other, they will transfer energy to one another. And if so, you've got a particle here, if it has enough energy, it can escape the water and become a gas molecule. And that's how changes of phase and how evaporation is the mechanisms behind evaporation and changes of phase. By giving these particles kinetic energy, they can escape from the phase in which they are in. So Hertz was thinking that a similar thing was happening here, that by giving this energy to the electrons, you're simply giving them more kinetic energy so they can just break free, as in this model of states of matter and phases of matter. So therefore, it seemed very plausible that if you shine a greater intensity of light, you're giving more energy to the electrons, and you're going to give them more kinetic energy. They already understood that a greater frequency of light would meant more energy. So by increasing the frequency of the light, these electrons would have more. They'd be quicker. They'd have more velocity, because you're increasing the kinetic energy. That made sense to them. And at low levels, you're not giving them as much energy, but you will eventually keep giving them that energy. It'll take some time, but their energy levels will increase, and they will eventually be able to break free. This was not exactly what they observed. And as Leonard was conducting his experiments, they threw up some very interesting results. So, firstly, there was a measurable minimum potential energy potential difference which stopped all electrons reaching the collector. And it didn't depend on the irradiance of the illuminating light. So the radiance is a bit like intensity of the light. It's linked to the intensity, but we'll explain that more in a few moments. Secondly, doubling the intensity doubled the number of electrons emitted. And so the doubling of the electrons emitted means a doubling of the current. So doubling the current. So the ammeter would be twice, the radial ammeter would double. But no effect on the kinetic energy. of emitted electrons. So in the classical model, double the intensity should have caused the kinetic energy to double, but it didn't. It increased the number of electrons being emitted. The maximum kinetic energy of the electrons depended on the frequency of the light. So higher frequency, more kinetic energy. Fourthly, there was a minimum of light frequency below which no electrons were emitted. So classically, if you're a lower light frequency, if you just kept shining it, you would eventually see the electrons being emitted and you'd eventually reach your current. If you had a low frequency light and you shone it really, really brightly, you would get the electrons being emitted. And they discovered this had no effect. You could get a low frequency light, you could make it as bright as you possibly could get it, and there would be no current. It made absolutely no effect. Whereas if you had, say, UV light and you were shining it at a very low intensity, you still saw the effect. Similarly, with that same idea, there was no delay in the emission of electrons, even at low light levels. So if the frequency of light was sufficient for electrons to be emitted, even at very low light levels, you were still getting a current. It didn't matter about the intensity. What mattered was the frequency. Now Leonard he couldn't explain these anomalies. He published his paper in 1905 and won the Nobel Prize for it because this was quite groundbreaking work, even though he couldn't explain it. Einstein took up the baton, so to speak, and looked at the experimental result, and he was the one who was able to explain it. Einstein proposed the following. So he proposed that light is quantized. So this goes back to Planck's idea of light being in packets. So it travels in discrete chunks called photons. So these are particles of light. Secondly, the energy of the photon is given by E equals hf. We've got our energy in joules, we've got Planck's constant in joules per second, and we've got the frequency in hertz. And he explained it by this analogy. So like a billiard ball, the incoming light particle strikes the electron, if it has sufficient energy, the photon will eject. The photon will eject the electron. If not, the electron stays in place. So those low energy photons, they'll strike the electron, they don't have enough energy, so the electron doesn't move. The high energy photons, say from UV light, they strike the electron and they send it off out of place, out of its orbit. Increasing the illuminating irradiance will increase the rate of the arrival of the photons, but not their individual energies. Now we can apply energy conservation. Oh, I don't want to take that way. Energy conservation to the photoelectric effect. So we know that E equals HF. So if we've got HF is equal to HF0, where this is the threshold frequency, plus the kinetic energy. What does this mean? So the kinetic energy is the kinetic energy of the ejected electron. HF is the incoming photon energy, and HF0 is the energy required to eject an electron from a metal. So say this is the so and I mean H and FO is the threshold frequency. Obviously in Hertz. So this is the minimum frequency of light, of radiation that's required to eject that electron. Now if you give it light with a higher frequency, i.e. more energy, that extra energy is going to go into the kinetic energy of the ejected electron. So we can graph this. And we find, a minute, it's a bit too steep. So this is the kinetic energy, is the energy of the photon minus the threshold energy, and we get this straight line. So this is our energy, and the energy would typically be in electron volts, and this is our frequency, and the point it intercepts here is the energy required to eject an electron, and it's also called the work function. And the gradient is Planck's constant. So this, what we just discussed, all of Einstein's ideas explained all the observations, but it was a huge leap to make. It led to the fact that light doesn't just behave like a particle, light is a particle and a wave. It's equally both. Young's double slit experiment with interference patterns had proven that light is a wave. It behaves like a wave, it interferes like a wave, it refracts, it diffracts, it reflects, it is a wave. But the photoelectric effect shows that light is a particle. It transfers energy like two billiard balls bouncing off each other. It's a particle. And this is a huge leap in our understanding. Einstein showed at this atomic scale, at this quantum scale, you've got this particle-like behavior. But when it's being when it's traveling in space, it's traveling as a wave, and at large scales, it is acting like a wave. Now we're going to go back, and we've mentioned irradiance, and so we're going to talk about irradiance quickly in more detail, and more precisely the inverse square law. So irradiance is so the energy of a beam of light depends on different factors. It's common for this to be referred to as the intensity of the beam, but in physics the term intensity has a very specific meaning, which requires the measurement of the profile of the actual beam, the cross section. So we are going to talk about the irradiance, which is a much simpler concept, and is defined by the letter I and is equal to the power of the source over the cross-sectional area. So this is the irradiance. This is the power, which is watts, and irradiance is in watts per meter squared, and this is the area, which is obviously meters squared. In square meters. So if you look at this here, with a very small power rating, say 5 milliwatts, the irradiance is of large value as a laser beam is a very small diameter. So you think about the laser beam, a very tiny little dot. It doesn't take a large power for the irradiance for that to be very big. Now, it's also just to note that when we talk about light, is always a light source, sorry, is always referred to as a point source. So say you had like a light bulb, and you would just refer to that as a point source. It's just like how in mechanics, how when you've got a mass, you would think of it as a point mass. So that's just a little aside. Now, what happens is, let's assume you've got a laser beam here, and you're shining it at some distance. How does that distance affect the irradiance? Now, if you were to plot irradiance by distance, you would get something like this. Oops, that's not going to be. It kind of falls off like this. And irradiance is inversely proportional to this distance squared. Where, so I equals k over d squared, where k is the constant of proportionality. And that constant of proportionality is in watts. D is the distance in meters, and this is irradiance, which is meters, which is watts per meter squared. Let us look at an example. So a commercially available pointer. So when you say pointer, it's kind of laser pen things that you would use to point at a screen during a lecture or similar. A commercially available pointer emits visible light between 532 nanometers, which is green, and 700 nanometers, which is red. And they have power outputs ranging from less than 1 milliwatt to 5 milliwatts. The cross-sectional area of the beam is around 3 to 6 millimeters squared at the aperture, and that spreads to 40 to 80 millimeters squared at 3 meters. Calculate the maximum irradiance at the aperture and distance of 3 meters. So this data is for the kind of range of different laser pointer pens that you can buy. So let's think firstly at the aperture. So we know that irradiance is equal to the power over the area. So for the maximum irradiance, we want to choose the maximum power available. So the maximum power available is 5 milliwatts. So it's 5 times 10 to the minus 3. And now, this is 3. We want the smallest area. So this is 3 millimeters squared. So we need to think here as to, this is millimeters squared, we need to make this in meters squared. So you need to be comfortable with switching from millimeters to meters squared. So it would be 3 times 10 to the minus 6 meters squared, because 3 millimeters squared is equal to 3 times 10 to the minus 6 meters squared. And that works out at 1.67 times 10 to the 3 watts per meter squared. Now at 3 meters, we're going to use this again, I equals P over A. So this time, the power is the same. So it's still 5 times 10 to the minus 3, but this time we are going to use the 40 times 10 to the minus 6, because as it travels, you're going to get the beams kind of, I'm going to exaggerate this, so this is the point, this is the laser point that sends out, oops, the beam will kind of increase like that, so it's going to be a wider cross-sectional area than at the source. And that then is going to be 0.125 times 10 to the 3 watts per meter squared. So I hope that helps.